right, what I think I want to ask you, so most of the teas finished this afternoon. I'll be able to finish up the rest of the tea and send you guys the template so you can start studying. You'll have no surprises. It'll be stuff that you've learned before in class, stuff off the in-class assignments, quizzes, whatever it is, you've seen it before. The only thing that's new is going to be this stuff, and I'm pretty much going to ask you to do those transformations and go through the calculations. So that's why I wanted to record and make sure that you had something with it. And the other one that you probably are not familiar with is the one with differential inequalities. I feel kind of nervous about skipping that, so I'm putting that on it's already on the T. It's the one where you had Euler's method, but then you had your differential equation bounded below by something and bounded above by something. How do you kind of track? The idea is that your exact solutions for these two easier equations on the bounds, you can solve for it and actually find those solutions and compare it to what you're getting for the numerical. It's another sniff check. There's multiple sniff checks. Okay, so just a reminder, we had these two nasty equations. They're totally made up. They don't reflect anything in reality. I just saw that my Hilbert Space professor was watching our YouTube videos. So I have to make him proud. But don't think I made him proud in the class when I was taking it. These were the two equations. And what we saw when we did that, just to remind you what we saw when we found that one equilibrium, there's only one equilibrium value, it's 0, 0. But the first thing you should do in this modern era is actually just run it. Run the stuff on a computer. And Robert did that, which is great. Robert started this class, he didn't want to open up Mathematica, but the first thing it is, ran Mathematica, looked at what it looks like. So that's a great transformation. You walked out of here somebody different. So what you saw is there was a circle, and it looked like when you started close to the equilibrium value inside the circle, which you already found was unstable, locally unstable, then it pushed the solutions towards the circle. If you're outside the circle, it pushed the solutions to the circle from the outside. So you can see that with the arrows that he had in his code. All right, so we're not picking up the circle. I think somebody asked me here, like, where's the circle in all this? How come it didn't show up in the equilibrium value? Well, if you set the derivatives equal to 0, you're only going to get a solution. You won't get that circle as a solution. You can. It's possible. I can show you an example where that's possible, but it might not show up as a set of equilibrium values. Okay, so what do we have to do? Yeah, but what we were doing to do that, what was the whole point? After the critical points. Like the 0, 0 that you guys did on the board. Right after that, I'm like, we have to go back to something in pre-calc. Polar coordinates, which everybody in here raised their hand and said, we love that stuff. So just recall, that's what we did. We transformed to polar coordinates. And for the first part of this video that I gave on the other day, we got the RDT is equal to R times 1 minus R squared. So, Nico, you're going to have to watch that. It's a lot of fun.
So,
it's already up.
Is there a specific reason why we're changing the polar coordinates? Is it because, like,
yeah,
circle?
Yeah, Robert, do you have that still on your computer?
So we're changing this polar coordinates because we know that these two are going to be have a circle.
Well, we cheated. We actually looked at the solution. We looked at the phase portrait, and the equilibrium. I can on an in-class assignment. If you put stable, I put locally stable. So all you know about that equilibrium, which is 0, 0, is that it's locally stable. You know nothing more about it. Unstable. Sorry. So he graphed the phase portrait, and what you see is a circle, unit circle actually, and that's happening. So our linearization didn't capture any of that. Right? So something wild is going on. The linearization didn't really include any of that. Push this back. Okay. So we're trying to figure out, like, that's not the real way you would do it. The real way is that you get out in the field, you don't have Mathematica, and you have to do everything by hand. Otherwise your platoon will die. Right? So the real way to do it is that you don't really know that 0, 0 is the only thing that can happen. And so you have to figure out that something else is going on, which I have no idea how you would know that from just the analysis we did the other day. There's no way, other than the fact that you have an x squared plus y squared, so you suspect something might be going on with circles. That might give you a clue to change it to polar coordinates. But it's not immediately obvious to me. I don't think I would think of that right away. I think it would be easier for me to find a way to use Mathematica out in the field. Huh? Just in case. Okay, so that's R. Recall that the points on the Cartesian coordinates, when you transform them to polar coordinates, you also have theta. And so we have nothing for theta yet. We just have an independent model for R, which we can solve. We can find the critical points. And just to recall, the critical points were R equals 0 and R equals 1. We don't have minus 1 because it's the same, it's the other direction. So we're just looking for R is bigger than 0. And R equals 1 is the formula for a unit circle. So there's your circle. It's the equilibrium point in polar coordinates. It's caught. Computations involved in this one. So I feel like this one problem that you get on the T should have lots of computations. We tried to make the T short so that you shouldn't be sitting there the whole time, because the one thing I hate is being forced to do lots of computations in a very short amount of time. So I pass that on to you. I don't want you to be sitting there for hours trying to get computations in there. I think most of them are straightforward. So we go back to this. The last lecture had a ton of computations. I stood up here like an old-fashioned professor. That's what we did. Like the professor would stand there and do lots of computations on the board and continue them the next day. So we're doing the old-fashioned way of doing things here. So you go back to that. If you recall, this thing had nothing to do with the differential equations. It was just a fact that came up when we took the derivative of R in terms of that related rates way of doing things. Recall? So that's how we got that. So this has nothing to do with the differential equations. But now I'm going to go and try to use this transformation. So let me box this off. It's number. Use number. So if I start with that one, I'm going to take the derivative. All of these are trajectories of functions of t. I showed you something, I was trying to show you something on Mathematica where I was trying to get it to do graph of polar coordinate equations that are functions of time. You guys remember doing parametric plot? So you want parametric plot with polar plot, and it just wouldn't do it. Mathematica's like, no, don't want to do that. So it gave me something really weird, even though I had syntax that looked correct in it. But what I would like to see from the solutions is that it spirals, and I could actually graph that as a trajectory. But the point of this is that x is a function of t, r is a function of t, and theta is a trajectory. So they're all parametric equations. So when I take the derivative as a function of t, I've got to use product rule here because each of these are functions of t as well. So you get first times the derivative of the second. Chain rule gives you d theta dt plus second times the derivative of the part of t. The reason I'm drawing that out is I remember somebody doing this on the board, and I'm like, I have no idea why they just use product rule right there. Why don't I? Just because all of them are functions of t, and you're taking the derivative straight across. Just like the man walking away from the lamppost. You had an x and a y, and both of them are functions of t. Same thing. Actually, it was the hypotenuse. Hypotenuse was x squared plus y squared. The x squared is a function. So that, you remember those, right? Good memories. Okay. Any questions so far? if I use the equation, okay, so what I got there is, I'm gonna do the same thing for y. I get first times the derivative of second is cosine. Did I get a minus sign wrong? The cosine's minus sign. Thanks a lot, Evan.
You don't want to use my laptop. I don't think I was supposed to help you.
Catch my minus signs. I remember the first test I had where I didn't do very well in real analysis at the graduate level. He had something with cosines and sines. Everything was ridiculously hard to me because we were proving things. But he said, I'm really disappointed almost the entire class got the derivative of cosine incorrect. Like, we're all graduate students. We forgot the minus sign. Okay, so that's got a minus sign in it. Get cosine theta t plus second times the derivative of the first, t. That's that nasty. It's about to get a lot worse. So if I punch a y through there, y is our y dx dt, so right here. You got to keep track of things and label them. This is bookkeeping. So this guy here, I'm going to call it, I don't lose it. So by that number, I'm going to punch that y through. I'm going to get r sine theta times this whole mess. And x dy dt equals r cosine theta times the mess that you got, which I haven't labeled, which I'll label in a second. That's dx2, where's dy dt right here. Right.
Sorry, I'm just wondering, what is the goal right now?
So I was actually just thinking when I was writing on the board, like what's the whole point of this? You want to get an equation for you're making a chain of variables. So remember when you were probably in AP calculus, you would do these transformations for an integral. And the whole point is that you want to take this integral, which had like squares in it, and make it look really nice at the end. So you did something wrong if the integral looks worse than what you started out with, that kind of thing. So we want to get to a place where this looks like an equation with theta, with hopefully only thetas in it, because the equation with r had only r's in it. That's kind of nice. I know how to solve that. So my whole idea is to come back here and come up with a nice equation for theta. But what I was thinking of is how good people used to be at this skill. That's my differential equations teacher was so good at writing these out, knowing what to do next. That skill, I don't have that skill. So if I was on a field and I had to do this, I wouldn't know what the next step is, that I'm supposed to do these things. I don't know. It's not a skill we have, but they didn't have our programming skills in Python programming. Our things have changed. So if you compute a lot, you kind of get a feel and intuition for it, and you'll be able to know this is what I'm supposed to do. But the end goal is to get an equation for d theta dt that's easy.
I think the second trig function of y dx dt should be cosine instead of sine.
Yeah.
Don't use
Patrick?
my laptop.
Why are we doing y dx dt? Because I thought we were kind of formulating what we have down there. Just dx dt, y dt.
Right. So I got this.
Right. 'Cause that's the thing that's just like always true.
That's always true. I'm going to use that in a second.
Okay.
Right? But first I need an expression for this and an expression for this. And here's, I guess, why you would do this substitution to get there is because you're trying to get thetas involved. Right? So you use, so this has x. Yeah, so x dx. So I need to kind of work out the calculations for what this looks like and what this looks like. So that's what's going on here.
Is that not our X right there and that not our DXDT right below it?
Yes, so what's going on here is when I did these two. Did I have this one wrong too? Should this be y here and x here? I think that's what's wrong. Right. Sorry. Writing the same thing over and over, you forget what it was. Let me go back and check. I'm just checking our work from yesterday, or Monday. It should be on Monday's work. Yes. No, this was correct. That came from r squared equals x squared plus y squared, so this was x dx dt. And this was, yeah, this was y. Keep this though, we're gonna use this.
Wait, so do we need to switch the other one?
No. No, the whole goal is that we're trying to get things to cancel out. So it's coming. So you need to keep, like, it's bookkeeping, so you need to keep everything I box off, you have to keep in your notes, because you're gonna pull them together. Just like when you did a U substitution, you start to do that quickly after a while, but at the beginning when you did it for the first time, you need to keep track of everything as you go along. Like, this was my U, and this was my, it's the same thing, but heightened up a level. Okay, so, yeah, the reason this is being done, just to preview, is that, so when I get sine squareds and cosine squareds, I am going to be able to cancel something out. That's the hope. That's where it's coming from. Okay, so coming. So now I'm going to take this equation and subtract it from this equation so that I can get sine squareds and cosine squareds to add up to be 1. That's what the goal is. That's how you use a trig substitution to get rid of something. You use the fact that x squared plus y squared is equal to 1, or r squared in this case, because r is not 1. Make sense? That's where it's going. Right, to kind of bring you back, when you used a trig substitution, it was when you had an x squared plus y squared in your equation, and then you'd shove in x equals r cosine theta, y equals r sine theta, and the x squared plus y squared would disappear just to be r squared. So that's where you're going with all this. I don't have an r squared yet, but it's coming. Okay, so y dx dt minus x dy dt, what that's equal to is going to be this mess here, subtracted from this mess here, subtract this mess here. So you have to keep track of your minus signs. And so what I get is minus r squared sine squared theta minus r squared cosine squared theta d theta dt plus r sine theta cosine theta dr dt minus r sine cosine theta sine theta d theta dt, or dr dt, sorry. Yes, it's going to cancel. That's the whole thing. They're going to cancel, and that's going to all add up to minus r squared d theta dt. And you should feel familiar to when you did trig substitutions. I don't know if you skipped that in AP Calc, but should feel familiar. when you did spherical and cylindrical coordinates. Which cylindrical coordinates and spherical coordinates is just a transformation from Cartesian to polar. That's really what you're doing in multi-dimensions. But actually, for the cylindrical, it's still the x and the y are only getting transformed. That should look really familiar from those days. I forgot you had that. So bottom line up front is that y dx dt minus x dy dt to minus r squared d theta dt. Like this. I just want you to know, like, with my these are my notes. You see me come in here and do stuff on the board without any notes. This is not one of them. When I'm boxing things off, as I'm doing things, when I'm repeating and writing it down and boxing them off, this is how I bookkeep. If you've been to my office, you know I'm not a neat person. I'm crazy. The office looks crazy. But when it comes to mathematics, and I know that I have to bookkeep, I know what to do. So this is what you have to do when you're, whatever your method is to keep track of things, this is what you're going to have to do. Right, Robert? Keep track, bookkeep. Keep in the books. But from the equations, y dx dt minus x dy dt, if you add the equations up, that's going to be equal to yx plus y squared, so in Cartesian coordinates. This part here, right here, is y dx dt, and the minus part here is x dy dt. Where that's coming from. I'm going back to the Cartesian coordinates. Again, if you remember, I actually remember doing this. It was traumatizing. When you do a change of variables, you keep having to go back to the x and the y, and then do something there, do some algebra there, and then go back to the transformation and do some algebra there. Those are like the nastiest problems I think we probably get in all of 255. I taught it. I remember. It's not a very loved section. All right, so everything cancels, and you get just x squared plus y squared, which is r squared. So from the box, I get r squared is equal to minus r squared d theta dt. So I'm going to just sub the r squared to this side. And that's how it works in 255 too. You do all these nasty trig stuff. Sometimes you even have to use a trig identity. Those are fun. And then you get something nice at the end. That's where that comes from. Oh no, it's -1. I have a problem with minus signs. My best paper ever was lots of computations in the finite field Z2, where 1 and -1 are the same thing. No minus sign errors anymore. So now, here's my coupled equations. thing there, that's the Verhulst model that you did right at the beginning with carrying capacity. It's independent of the theta, so you can actually solve it. And this one is just what you did when you were little. Integrate that, except it wasn't with a theta. This is an x. You integrate. So I can actually calculate this integral. What do you get if you integrate this with a function? This is the slope of a line. So it came from the line. Call that constant 2. And this one, I'm not going to do that by hand. That was something we did in the past. Let's see. But the way you did it is you separate variables, just to remind you, because I don't remember if Dr. Gross put something like this on the test, but you separate variables, and then you use partial fraction decomposition. Again, another lovely integration technique that you probably don't remember, but you used it. This goes to this side. Your plebes are doing this right now in 104, if they hopefully are studying for the T. Put the dt on this side, partial fraction that, integrate your partial fraction, and there'll be three of them, because you'll have a over r, b over 1 minus r, and c over 1 plus r, and you'll find the a, b, and c. Fine? Okay, we're not going to do that. The solution, I just integrated on Mathematica. And I got, I don't know if I even wrote it down. I didn't write it down, actually. Nico, you can actually just do a desolve on for this and just give me the solution. So we can actually find the solution for R. I might have done it for you last time, but I don't remember. So I'll have the solutions to both equations. And now what I wanted to do is, if I have the solution to that and it's a function of t, and I have the solution to this and it's a function of t, get Mathematica to plot the solution. These are closed form solutions. So I had something that was so nasty that I started out with. It boiled down to this. Just numeric, like desolve this one. Desolve r 1 minus r squared. Okay. We'll put the solution down there. And now I can get a closed form solution. So it is really old school math, right? Because we already saw the answer from Robert's code. We already saw it. Get it? You get it?
No, I can't.
I just desolve it, and then you'll get the answer.
Still
Okay.
I know we're back.
You can always do this by hand. Oh, I actually had a little note that you should take boards and do this by hand on the boards. Let's do it. So here's what I was trying to do on Mathematica. So this is going to give you some nasty function of t. This is a function of t. You can't parametric plot, just use parametric plot like you did in 55. That's where you did a parametric plot. Well, you can't do that here because it's in polar coordinates. So you want it to parametrically plot polar coordinates. So I thought I got the code correct. I plotted it, and it didn't look like what it was supposed to look like.
Does it matter if it's plus or minus? Or
No,
just
just take the positive.
so E to T is a fraction. So E to T on top.
Uh-huh.
E to T, and then on the bottom it's the square root of E.
Divided by?
Yeah, square root e to the 2t plus e to the 2c1, or c2 in this case.
E to the 2,
C2,
like that?
I guess.
Okay, so this is just a
Straight C2.
Lovely. So you can kind of see, like, this initial condition, if I have an initial condition starting at T0, R0, if I plug in 0 here, C2 is T0. That's my initial condition. And then I can figure out the initial condition here. Like if I put in T equals 0 here, I'm going to get, yeah, I don't want to do it. But you can figure out this. But you can kind of see what happens. Wherever I start out with this thing, the angle's going to get bigger and bigger and bigger. So that means it's, for an angle to get bigger, how do you draw these? This is back pre-calc days, limacons. You got to plot these things. Did everybody have to do that? Plot polar coordinates in a pre-calc class? What are they doing with you guys?
I think we have it.
I didn't touch polar coordinates in pre-calc.
Come back here and teach. We'll assign you Math 100. Let's do it. It's not a good start.
I have a math sweatshirt
Why?
that Fred found.
That's really funny.
Pre-calc is actually a very interesting class to teach. So if you do come back here, see if you can teach that, because teaching something like this is easy. You guys are math majors already. 103 is okay, because that's the masses. 100 is students who've got it again and again and didn't like it and don't get it, but they need to get it. That's where your teaching actually really improves. So here, if you started out at some angle, what that's saying is a solution saying that as the angle gets bigger and bigger as t gets higher, so it's going to wind like this. But the r itself, this is hard to see, but you can kind of like go through and say this is something like e to the t divided by, if you take the square root of e to the 2t, you're going to get e to the t. So something like r equals 1, approximately. So these are like a rough calculation. So the r is going to get spiraling out asymptotically until it gets to r equals 1. So I can kind of see that if I do limits, right? If I wanted to write this. And the other way around, if I started out with r that's high up here, and I start out with a t, it's going to spiral. But in this case, what's going to happen is it's still going to approach the limit 1, r equals 1, but it's going to do so from the outside. So it's going to spiral in to from the outside. So you can kind of see why that would be true. And that's exactly the picture that you got in Facebook trig. Beautiful, right? So I used to have students that didn't like to do these long computations. They hated proofs. Montclair, they didn't make them program. Why are you here? Like, this is a major where you have to compute, you have to write proofs, and you should actually be able to program. And they said, well, I get my summers off as a high school teacher. Questions? If I asked you to do parts of this on the T, would you feel comfortable going through the calculations? I'll guide you. Like I'll put in like,
If you broke it up for sure.
yeah, it's like, hey, show me why x dx dy dt minus y dx dt is equal to this. Do the calculations. Would you be able to feel
As
comfortable?
long as the equations are exactly the same.
You can get something slightly different, and you should be able to do it. I'll work it out
If it's easier
though.
and it comes out better, yeah.
Remember, you have Mathematica, ChatGPT, stuff at your disposal to check your algebra. So you can. That's what I would do. Is if I had it, like I would check my algebra that way. Also, like you could get something funky like this. This is really interesting. I think if you have dx dt is equal to y times x squared plus y squared, and dx is 1. Well, just like this would do it. You get funky things like this, where the unit circle turns out to be a set of equilibrium values. Every point on this your circle is an equilibrium value, so you get something really weird and happening. I don't know what happens with these, but here's a nonlinear equation that if you set it equal to 0, you get x squared plus y squared is equal to 1, which is the unit circle. So the unit circle is the set of equilibrium points. You could have a bunch of set of equilibrium points, which is probably not fun. So I'll give you something. It doesn't have to be the same equation where I'll tell you, like, this is what you should expect to see, so that you can do the computations. You should be able to do computations out of a differential equation class. That's kind of what's bothering me. Like, if I have to, I can sit down, turn on the Rangers game, and still be able to go through the computations. So that's a skill that I have. It's probably a skill that you need to have.